Good afternoon everyone, welcome to today's worked exam answer video. Today I'm having a look at a titration question from one of the OCR periodic table elements and physical chemistry papers, so one of the year 13 papers. We're using our titration skills. We are essentially using like a redox titration as well, but the redox equation has already been provided for us, so that's not something we have to write. So this is mainly a focus on the titration skills, so the calculation side of things. With this particular question, it's also making sure that we understand, I guess, the additional element, which is that there is sodium sulfite added to burger meat, and we're trying to find out whether a particular sample of burger meat has levels of the sodium sulfite that is above or below what the safety legislation says. So there is going to be an additional step at the end in terms of looking at what we've calculated for the mass of the sodium sulfite in the sample of burger meat we have, and then scaling that up to figure out whether it meets the regulations or not. If you are an AQA student watching this, you might have something similar in terms of redox titration. So the skills within this question are all very much relevant to you guys as well. AQA students, you might be asked to write this overall redox equation, and in order to do that, you would be expected to know that the MnO4- ions would be reduced to Mn2+ ions, but then they would tell you about the SO3 2- ions being oxidized to SO4 2- ions. Now, I'm going to use three colours, one for the sodium sulfite, or the sulfate ions within the question. I'm going to use one for reference to the burger meat. So it says food safety legislation allows a maximum of 850 milligrams of the sodium sulfite per kilogram of burger meat. And then we are only using in our experiment 525 grams of the burger meat. So that's where we're going to have to do a scale at the end. They collect the sodium sulfite from the sample of the burger meat that is extracted, and we make a solution containing the ions. Now, most redox sort of equations will be written ionically, so we are going to titrate against potassium manganate solution, but the potassium is not included in the equation because it's not the important ion. Essentially, it's spectating. Likewise, the sodium from the sodium sulfite, not the important ion, so in the equation that's not included either. Just wanted to make reference to that. And then once we have the SO3 2- ions in solution, that solution is then made up to 250 centimetres cubed in a volumetric flask, and that's sort of standard procedure for making up a standard solution. Then we're going to only use 25 centimetres cubed of the dilute solution in any one particular titration that we do. And so again, there's another scaling needed there. And then the pipetted solution from step 2, so our 25 centimetres cubed, is acidified with dilute sulfuric acid, and that's just to provide some H+ ions. Don't need to worry about that as part of our calculation. Titrated with 0.01 mole per decimeter cubed potassium manganate solution, which is the MnO4- ions there. Potassium's been ignored. And then it says that 12.60 centimetres cubed of the potassium manganate solution is required to reach the end point. Now, with more kind of redox titration questions, there's less of an emphasis on working out like a mean titer. But just like with an acid-alkali titration, you would be wanting to repeat this a number of times and then only using your concordant results get a mean titer. But essentially, that is classing as our mean titer in this question. Now, we are going to have to work backwards through the different steps. So you will have heard probably back titration as sort of like a method. I think that can put students off, make it sound more complicated than it needs to be. The only thing that I would take from that is that we need to work backwards through the information that we've been provided with. So the key parts of our equation are the MnO4 minus ions and the SO3 2 minus ions, and the ratio between those in terms of how they react. So I'm going to use those as like my kind of column headers, if you will. And then in the manganate one, we can work out moles because we have concentration 0.01, and we have volume, which I'm obviously going to need to convert into decimeters cubed by dividing by 1,000. So then the moles will be equal to, I'm just going to check that I've done that correctly for my conversion. So volume times concentration, 1.26 times 10 to the minus 4. Now, because of the balanced chemical equation we've been provided with, we can see that the manganate ions react in a 2:5 ratio with the sulfite ions. So therefore, if we know the moles of the manganate, we can just divide by 2 and times by 5. So I'll do that. And that tells me that I would have 3.15 times 10 to the minus 4 moles of the SO3 2 minus ions reacting with the manganate ions in the titration. Now, that is the number of moles within the 25 centimetres cubed sample that went into the conical flask. So the manganate went into the burette. That's how much was needed to come out of the burette and to react fully with 25 centimetres cubed of the sulfate ions. So what I'm going to then write here is that is the number of moles in 25 centimetres cubed. Because what we're then going to need to do, and again, see how we're working backwards through the information, initially those sulfite ions were made up into a 250 centimetre cubed solution within our volumetric flask. And then we've taken out 1/10 of that to do the titration. So therefore, I'm going to need to scale up the moles to show how many moles there would be in the whole solution. And because we used 25 centimetres cubed into the conical flask, and because we had a volumetric flask of 250 centimetres cubed, that is literally just me timesing by 10 to scale my moles. Now, that is the number of moles of the SO3 2 minus ions that we got from 525 grams of the burger meat. So what I'm now going to need to do is work out the mass of the sodium sulfite within that sample of burger meat, and then convert that into milligrams and then do our scaling. So first thing I'm going to need to do is work out the mass of the sodium sulfite. Now this is not the mass, sorry, the MR. This is where we need to not discount the sodium. Yes, it's not included in the ionic equation, but that's just because as an ion it's not directly involved in the reaction. But obviously because it has an atomic kind of mass, weight, AR value, we need to include it within our MR calculation. So sodium's 23, sulfur's 32.1, and each oxygen is 16, so that's 48. So the MR is 126.1. And then in order to get the mass of the Na2SO3, I'm going to do the MR times by the moles of what was in the 250 centimetres cubed. And that is obviously going to give me a mass in grams. So 0.397215 grams, and I'm only choosing to write it out in full because now what we're going to need to do to check if it complies with the safety legislation is convert it into milligrams, because that's what they've given us the information in. And I'm going to do that by timesing by 1,000, so that is 397.2 milligrams. Now that is the mass of the sodium sulfite in the 525 grams of burger meat. And we now need to know the mass in milligrams that would be in a kilogram, which is 1,000 grams. So I'm just going to again do another scale kind of factor, work out how many 525s go into 1,000, and then I'm going to times that by the mass in milligrams, and that gives me 756.6 milligrams of Na2SO3 per kilogram of the burger meat. And in order to comply with the safety regulations, we needed there to be no more than 850 milligrams. So because 756.6 is less than 850 milligrams, this burger meat complies with food safety legislation. And it is important that we make sure we're actually answering that part of the question. So in terms of the mark scheme, for the final mark, so this is 5 marks, we're getting 1 for moles of the manganate ions, we're getting 1 for the moles of the SO3 in 25 centimeters cubed, we're getting 1 for scaling it up into 250 centimeters cubed, we're getting 1 for the mass of the sodium sulfite in the burger meat, and then we get 1 for coming up with this figure of 756.6 and for making some sort of statement that that is less than the maximum permitted level. So without this sort of sentence, without this comparison, you would only have got 4 marks, which potentially feels a little bit harsh, but again, it's always just making sure we're answering the question. And that's how we would tackle a question like that. And as always, guys, if that's been unclear in any way, please don't hesitate to let me know so that I can clarify. Any questions similar to this that you want me to have a look at, again, just let me know. And remember, take care of yourselves. Obviously, work hard, but please make sure that you are scheduling in time for yourselves too. And if there's anything I can do to support you, please just let me know. Bye.